Hello, today we've got a brief video on a technique for solving linear homogeneous or linear differential equations. In general, a linear differential equation is going to have dy dx. It'll be plus or minus a function of x and y, so y times a function of x essentially, and then equals some function of x. If those conditions are in place, or if we could rearrange the equation until those conditions are in place, then we can apply the linear differential equations technique. It's a pretty cool technique, and without getting too deep into the theory, essentially it is a way of identifying and reversing the product rule. So first we need to get the differential equation into linear differential equation form. And again, the criteria are that we have a function, here we have y times a function of x, and dy dx added together. So then the trick, and again, this is something that is heavily based in theory. There's a proof for this in your text, but the idea is we're going to identify an integrating factor as e to the integral of whatever the function of x is that's being multiplied by y. And here's the thing, if you do this work correctly, then that integrating factor is going to create the product rule on the left-hand side. It's a pretty slick trick. So in this case, it's nicely designed because when I integrate 2 over x, I get 2 times the natural log of x, or negative 2 times the natural log of x, which is equal to e to the natural log of x to the negative 2, which is x to the negative 2, or just 1 over x squared. In other words, if I multiply both sides of this equation by 1 over x squared, then I will be able to integrate both sides, and you'll see why momentarily. So multiplying all three terms by 1 over x squared generates 2 over x cubed times y and 1 over x minus 3. So here's what this boils down to. What we see here is if I took the derivative of 1 over x squared, I would get negative 2 over x cubed. And if I took the derivative of y, I would get dy dx. So this is the product rule. If you don't believe me, I'm just going to take the derivative of y times x to the negative 2, and, well, it's exactly the same as what I have here. So I'm going to replace this entire mess with just the derivative of a product of the two functions, y and 1 over x squared. Sorry, I got ahead of myself on the writing here. So that on the left-hand side, we have something that is easy to differentiate because we're just going to apply the fundamental theorem of calculus. The integral of the derivative of this mess is this mess. Y times x to the negative 2. The integral on the right-hand side is nice and easy. It's just the natural log of x minus 3 plus the constant. And so in this case, the integral of that is just y times x to the negative 2. Multiply both sides by x to the 2, and then you get the general solution. So this is the solution to the differential equation written up here. There are ways of checking it, but again, this is just a quick little tutorial on the method or the process. The reasoning and the understanding and all that will again be left to your own devices. Pun intended. Alright, continuing on. This from the red-coded section, which is, again, as tough as it gets for the IB text. And so I thought if I could answer this question, then I can handle linear differential equations. And so the first thing I need to do is to rearrange this differential equation to see if I can get it to look like a linear. Of course it will, because it's in the section under linear differential equations. The technique, in case you've forgotten, I collect all the dy dx's over on the left-hand side of the equation, and then I factor out the dy dx, leaving me with x minus 1 over x times dy dx, and the rest of the stuff is left over. I simplify x minus 1 over x as x squared minus 1 over x. That way I can divide both sides by that term, which is like multiplying by x over x squared minus 1. So I took the 2 that's associated with the 2y, and I multiplied it by my x over x squared minus 1. So this becomes the function that helps me create my integrating factor. Remember, it's going to be e to the integral of that function. Now, hopefully your skills with u substitution are such that you can see here that 2x is the derivative of x squared minus 1. So this will integrate to be the natural log of x squared minus 1. And e to the natural log of x squared minus 1, x squared minus 1. Should probably include the absolute value, but I didn't see it in the final answer, and I don't think it really matters in the grand scheme of things here. So this means then that if I multiply both sides of this entire equation by x squared minus 1, I will have a product rule on the left-hand side. And conveniently enough, the x squared minus 1 divides out over here on the right-hand side. It divides out in front of this. And so I end up with x squared minus 1 times y. In other words, this here is the product rule where y and x squared minus 1 was the function differentiated. Again, you can check it. If you differentiate this function, you're going to get 2x times y, and you're also going to get the x squared minus 1 times the derivative of y with respect to x. So it works. Now I can easily integrate both sides here. See, this is actually the fun part. And solve for y. And that is the general solution to this differential equation. This differential equation looks so messy and challenging and complicated, but in the end it's just a nice, clean, rational function that I end up with. So how about that? Anyway, thanks for watching. Have a good life.